Okay, so what we've done is create and capture and drop several thousand of antihydrogen atoms, right? The equivalent to hydrogen in normal matter. And the answer is that as far as we can tell so far, they fall in the same way that a hydrogen atom would, in like normal gravity with, everybody knows, 1g of acceleration, 9.8 meters per second squared. So the results, and this is again the very first experiment, are consistent with the same behavior. But in physics, you don't really know something until you observe it. So this was the first attempt to actually observe that. What happens if I drop antimatter in the gravitational field of the Earth? So modern gravity is described by general relativity, Einstein's theory of general relativity. And in that theory, things in the gravitational field of the Earth should be attracted to the center of the Earth independent of their structure. That was the famous Galileo experiment from the Tower of Pisa, where he dropped a big mass and a small mass, and they landed at the same time. This is exactly the experiment we've done here with antimatter, to drop it and measure that it accelerates in the same way as all other types of things that we've ever dropped in the gravitational field of the Earth. So that's the main result here. We've actually done that experiment, observed it directly, and they agree. Okay, we're starting here with a drone's eye view of what we call the antimatter factory here at CERN, the antiproton decelerator and the Lena rings that provide antiprotons to the low-energy antimatter experiments. Okay, so now we're zooming in on the alpha experiment, which is working with the antihydrogen atom. We have to make antihydrogen atoms by synthesizing it from their components, which are positrons. We get positrons from a radioactive source, retrap some of the positrons, and then we're going to shoot them up into the vertical alpha G machine, which is where we're going to actually do the gravity experiment. So we trap some positrons, and they're just going to wait there for some antiprotons, which come from the AD and the Lena rings, pass through the beamline, turn the vertical corner up into alpha G, where they're again dynamically recaptured. So now, after some manipulations, we have a cloud of antiprotons and a cloud of positrons, and we want to make antihydrogen inside of what we call the atom trap, which is a magnetic bottle that will hold on to the neutral antihydrogen atoms. Antihydrogen atoms are formed by two positrons which collide in the field of the antiproton. One of the positrons gets captured, and you have a neutral antihydrogen atom, which is trapped because it's a little bit magnetic. Now, most of those that we make are actually moving too fast to be trapped. So they escape and annihilate, and that's what you see here. But a few of them will be trapped each time. Crucially, we can repeat this process any number of times and accumulate antihydrogen atoms by putting in more antiprotons, positrons, mixing them together in the same volume, and then holding on to the newly created atoms. For this experiment, we did this about 50 times for each point that we measured. Again, most of them, when they're formed by mixing the antiprotons and positrons, are not captured. So now the idea is to release them slowly. We want to release them to see what gravity does to them. So as we slowly release the barriers on the top and the bottom, some of the atoms will go out the bottom, some of them will go out the top, and they'll annihilate so we can detect them, and we can count how many went each way. Now for normal matter, hydrogen in this machine, 80% of the atoms should go out the bottom under the conditions of the experiment. The purpose of the current experiment was to test that behavior for antihydrogen, and that's what we've done. In fact, we find that the behavior of antihydrogen is consistent with the behavior of normal matter in the same conditions. Okay, so you and I and everything we know about, like this apple, are made of what we call matter, normal matter. But there's another possibility in the universe, which is antimatter, kind of an equal but opposite version of the matter that we know and love, which presumably was created in equal amounts at the Big Bang. By the way, we'd all be dead right now if this were really antimatter. The problem is these two things don't coexist, and for some reason, only this one survived the Big Bang. So we have a lot of questions about this stuff. Is it really the same? Is it the same when you look at it closely? Does it behave in exactly the same way every time? So one way to think about this is look at the gravitational effects on these two things. So Newton told us what happens when we drop this. What happens if we drop this one? Until today, nobody knew. This is the first time that we've actually been able to measure what happens if I make some antimatter and drop it. Now, I can't make an apple. I can make a few atoms of the simplest atom, antihydrogen, and that's what we've done in this experiment. We've created some of these anti-atoms, we've held on to them for a while, and then we dropped them. And the answer is, as far as we can tell, they drop in the same way to the current level of precision of this experiment.